This is the last new section for Chapter 5. We're going to be looking at other types of distributions. So far, we've looked at our binomial and like different probability distributions. So the probability distribution was the first type. We're going to look at multinomial distributions. Now, multinomial is more the generic term, um, or it just covers more types of distributions. The binomial that we looked at last section is actually just a special case of the multinomial, and because it's a special case, um, it's kind of like the bell curve. The Chebyshev's theorem will cover any kind of distribution, and when it's bell-shaped, you have the empirical rule that gets it a little bit more exact. So the percentages that we use, you can use Chebyshev's theorem, and say you go two standard deviations out, you get at least 75% of the data that falls below that curve. Well, when you know that it's bell-shaped and you go two standard deviations out, that's about 95%. So you can get more specific because you know a little bit more about the data. Same concept here is the multinomial is more the generic type. Binomial gets you a little bit more specific, and it's a special case for it. Okay, so here's the formula. So you got a lot of variables in there, a lot of numbers. It might start to scare you right away, but don't let it. So what you have to think of here is these x's, this x1, x2, x3, xk, meaning however far you go, these are just different items. And this is how many different ways that item can happen. You'll understand it a little bit when we look at the example. But this p sub 1 is the probability of x. So they go together. So make sure that you understand that these numbers, these subscripts, the 2, the 3, the k just means it could be 4, 5, 6, however high it goes, they go together. Okay? Here's an example on page 283. So multi, we're talking about more than two, where the binomial was when you can break it down and it's two separate cases, like there are two outcomes, a success and a failure. This is when there's more than just two. So in a large city, 50% of the people choose to go to a movie, 30% choose to go to dinner and a play, and 20% choose to go shopping as some kind of a leisure activity, whether it's on a weekday, weeknight, during the weekend. They break it down in those three items, right? So they may have done a survey and asked people, and they said, of these three things, which one do you prefer to go to? Yes, there are tons of other things. You could think of sporting events, concerts, all kinds of things like that. But in this example, they only gave them three choices. So we have 100% of the people, 50, 30, and 20. That adds up to 100%. If we randomly picked 5 people, what's the probability that 3 of them plan to go to a movie, 1 of them plan to go to a play, and 1 of them plan on going to a shopping mall? So here, this is the reason why it's multinomial. We have 3 different things. We have more than 2. We have movie, play, shopping. Looking at the formula. So we're basically only using this much, right? There's no x sub k. That doesn't go any higher than 3. So we're only using this. Okay? N is how many people we're picking, or how many events, how many trials there are. So there are 5 people we're picking. X sub 1 is the movie. X sub 2 is the play. X sub 3 is the shopping mall. So you go 3 factorial because x sub 1 goes along with the movie, and there are 3 people. That's what we're looking for. 1 for a play and 1 for the mall. Now you notice over here. So P sub 1 is the probability of event 1. Event 1 is a movie. The probability of going to a movie is 50%, so that's why 50 goes here. 30% plan on going to dinner. 20% plan on going shopping. The x sub 1, notice how these are the exact same numbers, so 3 is right here. X sub 2 is the same as it was right here, so that's 1, and x sub 3 is also 1. Do those calculations, you end up with, there's a 15% chance that out of 5 people, 3 of them are going to a movie, 1 of them is going to a play, and 1 of them is going to the mall. Rather than going over another example, there are more examples in the book. I think that's pretty straightforward, so I'm not going to go over more of those examples with you on here, but if there's anything you don't understand, make sure you write down the questions, make sure you ask them tomorrow. Or like I said, take a look in your book. There are a few more examples in there. The next one and the last one is called the Poisson distribution. And it's really useful when the number of trials gets to be extensive. What is large? You know, what do they mean when n is large? What is that number? I don't know if there's necessarily a set number that says once you get past 100, that's large. Once you get past 1,000, I think it more depends on what you're doing. If you're talking about how many raindrops land on our car, we'll think about how many raindrops come down in a storm. We're talking probably billions of raindrops. So is 100 a large number? No, not in that situation. If we're talking about, you know, number of kids in a classroom or something, or students that, you know, I may have during the day, is 100 large? Yeah, I don't even have 100 students. So it kind of depends on what you're talking about, whether or not n is large. And I don't know if, you know, unfortunately there's not a set guideline, there's not a standard that says this means it's big enough, this doesn't. Usually it's once it gets into the hundreds. Again, it kind of depends on what you're talking about. Okay? So the Poisson distribution can also be used when a density of items is distributed over an area or volume, such as, this is a really good example, the number of plants growing per acre. You think of how many plants are like for farmers, how many plants are planted. It's a high number, and it's over a certain area. Or a videotape. This doesn't pertain as much anymore, but if you remember, you know, a few years back, 8-10 years ago, when movies at the movie theater came in actual film rolls, and if you ever remember sitting there watching a movie and the film broke and you had to sit there and wait for them to splice the film back together and then restart it. Nowadays, I think everything is digital. There's some movie theaters out there, obviously, that still have film, but I believe a lot of them around town are digital now. But if you think about how many frames are in, you know, a 2-hour movie, it's astronomical. So that's another really good example. So here's your formula for it. The probability of X occurrences in an interval of time, or over a volume, or over an area. So again, you know, how many raindrops fall on a car, you would have to measure what's the area of that car. Where this new symbol, that's a Greek letter, it's called lambda, where lambda is the mean number of occurrences per unit. So we're talking about the average number of occurrences. So if we said, you know, in a per acre in a farmer's field, what's the probability that on average every acre has 20 plants that don't grow? Okay, that's kind of what we're talking about. So the way you write it is probability of X occurrences, whatever you're looking for, and then a semicolon, and you use lambda for the mean number of occurrences. So what's the probability of this many occurrences happening if this is the average. You kind of have to have an average. So, you know, in a given movie, the average number of times that the film breaks is 0.1. Obviously, you can't have 0.1 during a single movie, but over the course of 10 movies, if it broke one time, that would be an average of 0.1, 10%. Okay. The letter E, you should have that on your calculator. If you don't, you can use 2.7183, but everybody should have that on your calculator. It's just another constant variable. Okay. So here we go. We are talking about if there are 200 typographical errors that are randomly distributed in a 500-page manuscript. Find the probability that a given page contains exactly 3 errors. So in a 500-page manuscript, there's 200 errors. So that's our mean. If there are 200 of them and distributed throughout 500 pages, if we find that, that's an average of 0.4 errors per page. Okay, so you should always be able to find that average per whatever you're looking at. So what's the probability that any page has 3 of those? So our formula is this. X is 3, lambda is 0.4. So you use e to the negative 0.4. And then you take 0.4 raised to the 3rd power over 3 factorial. The chance that you have 3 of them on a single page comes out to be 0.0072. So a very, very small percentage that if on average you only have 0.4 per page, you're going to have 1 page with 3. If you have any questions on this, again, I'm going to cut the examples short. I don't want to go over too many if it's something that you understand right away. A lot of times it's a decision on which formula do I pick. So we've had our probability distribution, which you use kind of for your carnival games. We've had binomial, when you can narrow it down to just 2 options. We just had our binomial, and now we have this Poisson. So write down any questions you have. Make sure you upload your notes, and we will talk to you tomorrow.